All right, so students in my calculus class, as you have arrived to this video lesson, and it's a big congratulations to you because you are now making your way ready for another big concept and quite important concept in calculus. You are at the door to a different kinds of problems, completely different kinds of problems. So prior to this point, all of your work were primarily involving finding rate of change and all that, and that was the whole idea about taking derivatives and all that. And now we are beginning into a different kind of problem, completely different direction. But then eventually, at some point, you're gonna shockingly find out that the two concepts, what you've learned before about derivatives and what we're about heading out now, will be having a surprisingly close connection. So before our long journey starting ahead here, how about let me just now introduce for you the idea about the Riemann sums here. And this is just to get you into the idea, the big idea later on. So all about the derivatives that you have learned and finished up to this point is, to me, in the way how I see it, it's the first half of your calculus understanding. And now you are at that very first step into studying the second half of the other half of your calculus understanding. Okay, and so I have to keep bringing back some of the old memories a little bit, but so prior to this point, it was all about finding rate of change, as I said earlier in the beginning, the very beginning of this video, and it was all about the rate of change, and that promoted the idea of finding instantaneous rate of change as well as derivatives. But now, surprisingly, we're going to completely turn away from that. We are beginning our way into studying about areas, actually. So the whole later halves of calculus learning, of your calculus study, is all about finding areas. So Riemann sum is what I'm starting out first, but believe me, we're at just the very beginning, and so we're gonna have to step by step, and throughout many lectures later, you're gonna understand what exactly is finding areas in calculus. And it's a whole fun and fascinating world waiting for any of us out there. Okay, so let me start right here with the idea of Riemann sums first of all, because it's a very important the building block for any of us later on to get further into finding areas in calculus, the kind of formal problem, and essentially the term you might have heard somewhere here and there before formally learning it, the integrals. Okay, so let's now really get right here into a Riemann sum and find out what that is. And so, as I said earlier, we are making our way into studying areas. So, and there are other concepts that eventually make you understand why finding areas, being able to find areas, is so important. But now, let me promote the idea of Riemann sums as following. And this idea I'm bringing up here is not the only application where you can see Riemann sums to be applied. And then, so let me promote the problem with, how about we are given a function, f of x, to be, let's pick a simple function, x squared. Okay, this is the function that anyone viewing this video should be well familiar with, and nothing surprising about this function. And if you're thinking about the graph, and as a matter of fact, speaking of graph, I do highly recommend that at this point when you arrive at this video, make sure you know the graphs of, the graph of all of the common functions. The linear function, a quadratic, a simple quadratic like this, an e to the x function, and an e to the x function, a logarithm function, and for students who are heading out for engineering major or physics field, know the sine or cosine function, or generally the trig functions. You gotta nail down all of those basic common functions before we can head out to the, so that we can move on smoothly with this. Okay, so now we have the function x squared here, and so that's why I said we need to know the graph. So for this graph, and I think I should make it even bigger because we need to see the picture as clearly as we can. And I am not going to draw the complete graph of this particular x squared function. I am going only, because everybody knows that x squared function is that nice parabolic shape that's going like this. And I'm not an artist here, so forgive me that my graph is not the best looking graph out there, but it's a parabolic shape like this. Or in short, it's a parabola. Okay, so I'm not going to worry about the other part because that's not really what I plan to show anyone. But let's just focus on the part where the graph is on the positive x values. So we only need to focus on that part where x value is positive. And you will get the generality of this kind of work at the end of our discussion here. So don't worry with me. Don't worry about why I completely ignore the other part of our parabola here. So that's the parabola famously known for the x squared function. X squared function gives me this graph, and I only want to consider the part where it's positive, I mean non-negative and up. Okay, I mean starting from 0 and up. So now this is the part where I famously, I mean I've been traditionally starting out with my students here. How about starting out at zeros here, and I'm gonna pick an interval. So basically here it's just an interval that I pick from 0 to 1. So we have a graph. That's the generality right here. So maybe let me switch over to the other board of mine. And along with what I'm bringing up here, I'm also going to bring up a generality. The idea now is that we have a function. We have a function. And the curve could be a curve up and down right here. Okay? Some function that's being graphed from some function having a graph being an up and down graph. Just like the x squared function we have had. And then that interval I mentioned earlier from 0 to 1 is generally just some interval from A to B. Okay, so we have a function up and down, continuous function, of course. And then we're going to turn our focus, narrow our focus into an interval specifically given. And so that interval in our problem here now is the interval that I chose for this lecture from 0 to 1. Okay, and so now here's a challenge for any of us, and it was a famous problem back then, back in the ancient time, and surprisingly, it took mathematicians thousands of years to develop this idea. Okay, so anyone arriving at this video shouldn't be surprised that when we end the interval up to here, okay, then you can plug in a value into, this end point of the interval, you can plug into the function and you get a height of the function. So you got a height up to here. Okay? And then when we're substituting the left end of our interval into the function, we got a left end point. Okay? And so it has a height being for this function 0. And then this right end point has a height 1. And I made it really big, so that's why it looks pretty high in my picture over here. But that's just how it is. This height is f of 1. Okay? But now the challenge we want to do is, how about I want to find the shaded area. So now I'm going to be shading the area. So look at the description here closely. Look at the description here of the area closely. The area is between the curve itself, the graph of the function x squared and the x-axis. And that's why it's so famous. It's anytime you're having a function, you definitely will have a graph. And then now the graph will be, and then so we're trying to find the area, okay, the area between the curve f of x, see, between the curve f of x and the x-axis, okay. And then of course furthermore, so that's just the vertical side. It's being restricted. It's being limited in between the x-axis and the curve itself. And horizontally, it's being in between. Okay, so it's shaded from x equals 0 to x equals 1. So think about, so on the side way here, on the horizontal side right here, then we're talking about, we're starting our shading from x equals 0, and we're shading it to x equals 1, and that's what it is. So this is the total, like a total description of our area that we're drawing here. Okay, and so now let me swing to the other board again to conclude out that generality. And of course I will get back to that general idea much later, but now along the way here, you see, so we have a function and a given interval. The function, supposedly a continuous function. So the function will make some area between the function itself with the x-axis. The x-axis is here. And so now, and inside the given interval, we are attempting to find that area. We're attempting to find that area. And so that's the generality here. But see, it took mathematicians a really long time to eventually come up with a solid method to find the exact area like this. I mean, I'm talking about precise, a precision, a good precision here. Okay? So why is it such a challenge? Because now if we're looking back at this problem, for any of us arriving at calculus, finding the area of a rectangle. No, so I need more board space, so I have to erase this. So we just now know our goal, that we need to find the area inside of that picture. Okay, but see, for any of us, of course, I mean the viewers of this video and my students here watching this videos with me, finding the area of a rectangle is easy. Length as an L variable and width as a W variable. So area for something like this, length times width. Okay, that's straightforward. Okay, even the second grade kid is starting to learn about these things, I believe. So nothing surprised about how to find area of a rectangle or something square shape like that. And then when we grew a little older into get into a little more advanced into math, then we start learning about how to find the area of a triangle. And then with some shape like this, not a nice one like a rectangle, not easy as a rectangle anymore, but we can still have a definite formula. So we draw a height, and then that height drop to whatever, because the idea of the height here is it drops from a vertex to the opposite side, and that opposite side is referred to as the base. So in the end, we still have a definite formula. Area equals 1/2 of base times height. And I wrote height times base, it's the same as a product. So we still, in the end, even though we moved out from rectangle, but we still have a definite formula for this area. And then we went on to higher math prior to calculus, before calculus, and we came to finding areas of some other shape like a parallelogram. Okay, and then ultimately we arrive at circle with a center and then with a radius. And so with even something like this, we use a formula that was known with ancient mathematicians in a long time. Area of a circle is pi r square. That gives us the exact value for the area of this nice round shape right here. So in the end, all of these common shapes, we know it all. We know the area formulas. But now, this shape now becomes a challenge for us. There isn't any formula for something like this. There is no formula for something like this. It's not a triangle. No, it's not a triangle. It's not a rectangle. Nope, it's not a rectangle. It's not any of the common shapes we have seen. Okay, and so that's the reason why this problem started out, as I said, long ago, back in the time where, back in the ancient time, and it took a really long time. If I remember correctly, in a history book I read about math, and it took about thousands of years to eventually come up with a solid method to find the answer for that kind of area. So just want you to know, it's this area here, we will be able to find that. It's just not any of these. We won't be able to have a definite formula like for the area of a circle or for the area of a parallelogram or a rectangle, whatever. We won't have any of the formulas at all. So this is how. So now let me, as we starting now getting into that, and we understand our goal here, I gotta show you how clever the mathematicians in the past have come up with. So yes, we know that our goal here, and I have to erase all the shading here because we know already that that's our goal. All right, now I'm going to keep my graph and make a completely different picture over here. This is what we want to do. So now think about at the time where we never had calculators, we never had advanced computer like what I'm using here with on my board, on my table here. Then here's the thing, and this is also the idea we have to start going through right here. Mathematicians in the past cleverly, and see, at this point, I keep referring to past mathematicians because I love to give credit to these people in the past that they come up with this. I was a learner, and now I'm passing it down to anyone viewing this, and the big credit went back to all of the people who came up with this idea right here. So instead of finding the exact area back at that time, here's how they developed that. First, think about we approximate that. We're not going to think at the point of the original point when we first had this problem promoted, then we come up with the idea of approximating. So here's how we're doing it. So in the end, from 0 to 1 is an interval. It's an interval. So we're going to break it down. We're going to break this interval into sub-intervals. Okay, so let's do it like this. See? So right there, and now as I put down my little tick marks in between the 0 and 1 here, then now I produced about 4 sub-intervals already. Okay? And so now, usually over my years of teaching, and specifically teaching into this idea of operating with Riemann sums and all that, and getting anyone ready for the later kind of calculus work, then I usually start out with, so my letter n right here is to represent an n here equals 4. Here I'm talking about 4 sub-intervals. Okay? So that's just for start. And it's my recommendation. Even though we can stay with less, but for a problem like this, having less interval is not fun. So let's do with 4. Okay? And so now I'm starting out. It's just a choice right now. And 4 sub-intervals. It's just a choice. So again, back to what I was saying, the big idea now is that this total interval window right here that we're trying to obtain our area shaded inside of the curve here is now broken down into 4 sub-intervals. Okay? And to be honest with you, with any of you viewing this video, the original idea here is that the intervals that we're breaking down right here, the intervals that we're producing here, did not necessarily have to be equal width as well. Okay? And I'm using that term equal width because you see each of the sub-interval here, any interval has a length from where it starts to where it ends. So this is the width of our total interval from 0 to 1. And then so now just like what I said earlier, each one of these small intervals being the sub-intervals of our total interval here, the original idea did not require them. And that idea still remains in these days, but it's for the people who want to study the advanced math. So for us here as a starting of calculus, I just only want to briefly introduce that originally the intervals here were not required to be at equal length or equal width. Okay? But now, it was proven that if we stay with equal width, so now we're going to purposely choose equal width. Okay? Nail that down for me. It was not originally required to break it down to equal width sub-intervals, but it was eventually proven. And of course, for us here being the beginners into this, I don't want to bring up the proof, and it's making the lecture a little boring and kind of dragging. So I just want to point out that it was then proven that it's going to give the exact same result if we decide to go with equal width. And hey, it's making life simpler for us. It's making life easier for us if we go with equal width. Okay? So that means I'm aiming at each one of these. Of course, forgive my hand sketch that I might not be able to make the exact equal widths here on each of the sub-intervals, but they are meant now, they are intended to be equal widths as we purposely chose. Okay? So this is something that we chose. chosen to be like that. Okay, so 4 equal widths. So now this is also something that's chosen. And then now with the number of chosen subintervals, we're gonna make the next choice here is to go with equal width on each of our subrectangles. Subintervals. Okay, and so now here's the first impact. And so now, before I mention the impact, I was saying a little bit, let's create a name. So in the end, each interval here is a difference in the x values. Okay, take a moment to agree with me to find out if you can agree or not. Each little subinterval here in the end is a little change in x value, or a little difference in x values, because that's the width, or it's the length of the interval is found by the difference between the right end and the left end. Okay, and so now any of these space here between 2 tick marks here on my sketch is now referred to as a delta x, and that's now being, so delta x is the famous symbol from now on we use to indicate the width of each of our subintervals. Okay, and since they're all equal width, so this space right here, I haven't pointed out how big that is yet, but should be equal to this space here, and it should be equal to that space. And that's why there's no reason to name them traditionally or originally. Again, this is delta x1, the first little space right here. This should be delta x1, the first width, and then it moves on, and then as we move on to the next one, delta x2 for the next space. But since we purposely chose all of these little subintervals to be equal width, and so in that way, they are all just equal one value, and they're all equal one another. And so that's why, so now each of the little space here between any 2 adjacent tick marks here, that is the width of our subinterval, and I call that, it's a delta x. Okay, and so at this point, now I'm really going to get into that. So let me now put aside the generality that I was about halfway talking into it, probably just about a quarter way talking into it. Let's stay focused on the problem I brought up right now. So, because we chose equal width, and we chose 4 subintervals in our total interval between 0 and 1, and so that means we can actually think about it. We can actually calculate how big each of our width is. So, isn't it the total interval from 0 to 1? The total length of the interval from 0 to 1 is 1 minus 0, the ending of our interval minus the beginning point, the left point of our interval. And now that's the total length for the interval between 0 and 1. It takes length 1. But now each one of our delta x here as a subinterval. And there we got 4 equal width subintervals. So in that way, it makes perfect sense now that we're going to divide by 4 the number of subintervals that we decided to break our total interval into. Okay? So remember, we can only do this because we purposely chose that all of these little subintervals are equal width. Okay? So as a generality, let me kind of put a remark here. So in general out there, back to the picture that I already erased here about the generality of this kind of problem. We are approved to use equal width because it doesn't change the result at all. And so doing it that way, then each of the equal widths here is going to be b minus a. B is the final point of our interval. Subtract a, and that difference there is divided by n. The number of n is the number of subintervals that we targeting for, that we are choosing, that we have chosen to break our interval into that many subintervals. Okay, and so in this problem, each of our subinterval has length or has width 1/4. Okay, at this point, calculus students of mine, I highly recommend that be able to work with fractions. But in case you're still not comfortable with fraction and love to rely on your own calculator, then this 1/4 is the same as a 0.25. Okay, so now that means this space is a 0.25. I'm talking about the space between them, the difference between these two adjacent tick marks right here. That's a 0.25. That is another 0.25 between these two. This is another 0.25, and maybe forgive me if my drawing was not so perfect. And then this is another 0.25. So all the 4 different little 0.25s together made up our total intervals being length 1. Okay, and so now in that way, after that, I am heading out to the next understanding. I highly recommend that my students doing this anytime you are about to do, and we didn't get to the idea of the Riemann sums yet. We're still building things up step by step like that. But so now you understanding that one total interval, we're breaking it down, we're chopping it down to sub-intervals. This is the number of sub-intervals we decided to go for now in this particular activity. And then because of that, and we also chose an equal width. And so each one of the sub-interval is at length 0.25 or 1/4. And so now I recommend doing this. We're going to redraw the whole interval from 0 to 1 without the graph. We're only going to redraw the whole interval from 0 to 1. So 0 is here at the start, 1 is here at the end. Okay, and so in that way, yes, halfway is here, quarters are here, because we broke our interval from 0 to 1 into 4 sub-intervals. Okay, and so as I said, you don't need to draw the whole graph here. I highly recommend to draw again only the interval itself here, with the 4 sub-intervals being partitions inside of that. So each of these are called the partition points. So these points itself right here, now officially we can call them the partition points. Okay. All right, and then shortly I'm going to have to erase that term to make more space right here. But see, so now mathematically, if this is 0, and each of the space here is being 0.25, then you can think about this exact point, this exact partition point right here is 1/4, or in decimal 0.25. Either way you want to write it. I write 2 conventions there. Okay, and maybe at some point eventually I'm going to give up one convention and only stay in one. Okay, and so the next point over, think about it, it's 2 spaces like that, right? 2 of the 0.25 spaces over to the left of the starting point on our interval. And so it makes sense to be a half right here, am I correct? Or think about it, it's 1/4 plus 1/4, it gives me a 1/2. And so, or this is a 0.5 in decimal. 2 different ways you can understand. Okay, and then that one here is, of course, it's 3/4. Because it's 3/4 spaces away to the right hand side of our starting point on the interval here, on the total interval. And so now this is 0.75 in decimal, if anyone prefer writing it that way. Okay, 0.75 here. And of course another 0.25 space added on to that very last one, and we ended up with our final one. So many textbooks also indicate this is A right here, this is B, our final point. A is the starting point of the interval, B is the final point of the interval. I recommend knowing these values right here, and it's a very good habit that you draw separate out your own interval in a separate picture, and then draw and calculate down all these partition points successfully. It will help big time in the next step when we're getting into doing the Riemann sum work. And of course, I keep talking about the Riemann sum work, but we haven't officially gotten into that yet. Okay, so now I'm getting back to the other picture. And now I can fill in this value. Let me erase all of these extra writing here because we're done with those. All right, so those partition points are here. But the picture here is a little smaller and too squeezy, so I only go with how about decimals here, because I understand for some reason a lot of time, even for my students who arrive at calculus, I see there's still a bigger majority who prefer working with decimals. But I still highly recommend working with fractions. So this is a 0.25. It's that particular spot, and then this spot right here is 0.5. And this next partition point here is 0.75. Okay. All right. So here's the idea. This is the idea that drives anyone into the Riemann sum, and by the time when you look back, you're going to be surprised what you've learned. Okay. And this is and as I said again, this is the idea that I want to give it all the big credits for the past. I mean the past mathematician who came up with this. Okay. So, how about in this first interval, or actually, the first interval is a little unclear here. So how about, I'm going to pick any one of the two middle one here. How about the third interval? So from the left to the right, that's the way how we always read any graph. So from the left to the right, I'm going to pick the third interval over here. So interval 3. This 3 just indicate the sub-interval number 3 right there. I'm going to another choice to make right here, okay? Another choice to make. But once you made that choice, you got to stay in that choice. On this third interval, I'm going to decide to pick, because any interval has left endpoint and right endpoint. So on this third interval, 0.5 is the left endpoint, okay? And 0.75 is the right endpoint. I'm talking about endpoints. So my board space here is limited, so allow me to skip the word endpoints, but 0.5 is the left endpoint of my subinterval number 3. 0.75 is my right endpoint, the right endpoint of my subinterval number 3 here. So now back to what I was saying earlier. I made a choice actually. It's a choice. I made a choice that, hey, for this interval, let's pick left endpoint. Okay? Let's pick left endpoint. And so, in the way it is, if we pick left endpoint, and that means 0.5 is the left endpoint. So now, but what's good about picking an endpoint? So now once you made the endpoint, and in this problem I said I chose a left endpoint, then we're going to take that left endpoint, substitute that into the function. The left endpoint is 0.5. Our function is x squared function. Substituting that into the function, we're going to end up with 0.5 squared. Whatever it will come out, it's just a value. But here's the impact. I highly recommend you start practicing on working on your skill about looking at picture, looking at a graph here. But well, as a numerical value, I have nothing to say. But as the graphical meaning, this value that came out from 0.5 square here is the height. The height that's from this left endpoint, that's when you draw straight up and hits the graph. That's the height right there. Okay, the idea is still easy, right? All right, so now here's how I'm doing it. So from now, that's the height. That's the height. Now from that height here, and remember, we got that height because we chose the left endpoint. We chose the left endpoint on this interval number 3, and right now I'm only focusing to this interval, sub-interval number 3 right here. On this sub-interval number 3, I chose left endpoint, and I substituted that left endpoint into the formula. I mean into the function. And so the formula of the function gave me the final value right here. But the final value, the final output on the function here is now graphically understood as the height. So we kind of mixing between numerical and graphical here. But now from that, now I'm going to draw over as a rectangle. All right, so what's special about that rectangle of mine? That rectangle has, so for that rectangle number 3, it has the width for that, as far as value, 0.25 space, right? From 0.5 to 0.75, it's a width, 0.25. And this is the width, okay? But then the height is f of 0.5. The height, so this is the height. So I open parentheses to explain it. This is the height of our rectangle number 3. All right. So now what if I multiply these two? And at this point, think completely as a picture. So right here with that area, with that little picture I drew right here, we've had a rectangle. Width is a 0.25. The height here is whatever produced by f of 0.5 right here. Height, width. So if we multiply height and width together, ladies and gentlemen, we have the area shaded inside of that. The area of that rectangle. It's a rectangle now, and it's the area inside of that little rectangle. All right. So it was a step-by-step process. But now back to what I said earlier. On this rectangle, on this subinterval, the whole reason we came up with that rectangle now is because we chose the left endpoint, and from the left endpoint we obtained the height of that rectangle over this space right here. Okay, so hopefully everybody is all good with that. And so that space here, that height here, is produced by the left endpoint substituted into the function. We got the height, but the height here is the height created by the left endpoint. But so now, I did also say that once you have chosen to use the left endpoint on this specific subinterval number 3, then for the rest of all the other subintervals, we're going to stay with left endpoints. Okay? And so now, I'm going to quickly move out to the other board and note down what I've had right there. So, allow me to do this. So far I've had rectangle number 3, RECT 3. RECT is short for rectangle. So for rectangle number 3, this is what I did. I've got the height here being point f, the height that came out from f of 0.5. This is my left endpoint inside of that interval. So this is the height. Okay, that's height. And then I'm going to multiply with the width being 0.25. This is our delta x right there. Okay, the height multiplied with delta x, or this is another way of seeing it. It's the width of the rectangle. Okay, we got that number, the rectangle number 3 nailed down. Yeah. Okay, so now from that point, why don't we look at the fourth interval? So now interval number 3 is done. Let me just shade it in. Okay, so fourth interval is here. That space between 0.75 and 1. So it has a width here being 0.25. And trust me, at this point, anyone who's on gear with me, who's pretty on track with me here, will understand clearly that we all have equal width. So it makes sense that the width of that fourth subinterval must also be a 0.25. But now in the same rule, I am going to pick the left endpoint. So in my fourth interval right here, the left endpoint is right here. So now let me erase this. Now left endpoint is here. Left endpoint is here. Right endpoint is that last point of our total interval. Okay? And I'm talking about specifically right now, I'm talking about the fourth interval. Okay? So in that way, very similar and the very same work we have done for rectangle number 3 earlier. So now think about it. If I pick the left endpoint again on the fourth interval and substitute that, so 0.75 is the left endpoint on the fourth interval, and substituting that into the function f of x, I'm going to obtain, well, the value can numerically be calculated as 0.75 all squared. But what I want viewers, what I want my students to see here is that this is going graphically understood as the height, because when we substitute that value into the function, then it creates a height that will reach to wherever the graph stays right there. Okay, and so from that height, so this is now the height of our interval, and then from there I'm going to draw a rectangle over. And so now here I have another rectangle, and this is rectangle number 4. So as I keep saying, this is height, okay, of our rectangle number 4. But what's the width? The width is, of course, 0.25 again, which is the same as the delta x that we've been looking at. Okay, and so now again think about if we multiply these two values, the function value at 0.75 and multiply with the width, this width right here, that gives us, as a picture here, the area of this fourth rectangle. So rectangle number 3 is here. Rectangle number 4 is here. Okay, and so now, so that's what I just did right there. The height is produced by the function value at 0.75, and then the width is delta x. That's for rectangle number 4 here, and that's how I just shaded it. And so in that way, now let me put that on my chart here. So for rectangle number 4, that's the last one of the picture. So the height there is f of 0.75, and then the width there is a 0.25. Okay, so there's again this height, okay, and this is width, and of course that's the same as delta x. Okay, and I'm not saying so for now, so for all I want people to understand is that we have two separate little rectangular areas completely inside of our picture right there. So this is one area of the rectangle number 3. This is a separate area of the rectangle number 4. Of the sub-rectangle is number 4. So now we're not only having sub-intervals, but what we have produced there in the picture is a whole bunch of sub-rectangles. Okay, and so now, and the reason I stay with I started out with rectangle 3 and 4 first because it's bigger, it got more areas, more space for me to work with. But so now, if we're now looking back into the left side of our graph right here, and it's just the same concept. Now looking at interval number 2 right here, left endpoint. So it looks like for now, left endpoint is what we stay as a rule. On each interval, we choose the left endpoint. On each interval here, we choose the left endpoint and substitute the left endpoint into the function to obtain the height. Okay, and so on this particular interval here, and of course it's interval number 2 from the left to the right. So left endpoint is here, the 0.25, and the right endpoint is that 0.5. All right, so again, this is what I'm doing. I'm going to take the left endpoint and substitute that into the function. So 0.25 being evaluated into our current given function. And so numerically as a value, it's 0.25 squared. Okay, and with our calculator, and we don't need to get that numerical value at this point yet. And so I'm leaving it there. So that gives me height, because it's very similar. It's the exact same argument I've been making for the two pictures earlier. If we substitute 0.25 into this function, it gives me that height from where our partition point here is, and hits to the just stop right when it lands on the graph like that. And that's why the reason I chose to do this after these two ones, because it's a little narrow space here, so it could be a little hard to read for anyone viewing the video. So that's the height, being a small little tiny height, and then from there I'm going to draw over as a rectangle. Okay, and so of course this is rectangle number 2 here. And then this rectangle has the same width, 0.25. So the width of this rectangle, the width here is 0.25 again, which is the same as that delta x that we were calculating. Okay, and so again, recognizing this picture is also a rectangle, what can we do with this? Multiply length or height and width right here. Height multiply with width, we're going to calculate, we're going to have the area. So this is rectangle number 2. I write that, the little label number 2 right here. But height times width right here gives me the area that I just now shaded inside of that. Okay, and so again, I'm going to swing over to my other board right here. So for rectangle number 2, okay, we got the height here is f at 0.25, okay, and I'm going to multiply with the width 0.25. Okay, so I got 3 separate columns right here. Allow me to use columns to separate out. Okay, so what about the very first interval, the interval number 1 right here? So at this point, it's the same generality that hopefully anyone viewing the video has already drawn out. So we're going to do the exact same way here. All right, so for the first interval, this is going to be left endpoint, right endpoint is here. That's right endpoint. So in that space, again, the rule we're going now, we set for ourselves into that rule because we chose it. Okay, and so that's left endpoint, and this is the right endpoint. So we're going to take that left endpoint being the 0 this time. We're going to substitute that into the function. Okay, and that gives me a 0 square, which is easy enough for anyone to see it's 0. So what does that mean? We will have a height, but the height is right there at 0. So the rectangle we have here is right there, kind of right there. It's not anywhere rising up at all. It just stays right there. So it's a 0 area rectangle. So the width is the same, being 0.25, and that's the same as the delta x that we've been talking about. Okay, and to find that area, height times width, height times width, that gets me the area. And so in this case right here, for rectangle number 1, okay, rectangle number 1, f of 0 multiplied with 0.25 being the width. Okay, height times width, height times width. So, all right, and that's what I was saying earlier. See, for rectangle number 1, and I apologize for the very narrow space right here. So the height is f at 0 multiplied with the width. Okay, so now I will erase and rewrite all that. But the idea now is that, so I was saying earlier, as I was saying earlier, before we got into making any of these drawings, we were approximating area. So now it's time to go back and understand further what it meant by that. You see, instead of getting the exact area between the curve here and the x-axis, but now at least this is what we can do. I have produced the area for this angle triangle number 2, this triangle number 1. Not triangles. I apologize for saying that. I meant rectangle. So we found the area we can find. We didn't find it yet, and we didn't calculate it yet, but we can find the area of this rectangle number 2. The area of this rectangle number 1 is easily understood to be 0, and this area of the rectangle number 3, and this area of rectangle number 4. So why don't we just add them up, at least cumulating them up? I'm starting to use that term, cumulating up the areas. But for now, we're accumulating the areas of each of all of the sub-rectangles that we are shading here. Okay, so accumulating it is the term, and accumulating now producing for us a sum. I'm getting into that way where I'm talking about the sum right here. So how will that work? On my other board, here's a final formulation, and hopefully you can always roll back to the earlier point of this video before I erase this to copy it down. But so now accumulating means the area of the very first rectangle is the height is at the f at 0, multiplying with the width 0.25. That's rectangle number 1. And then the area of the rectangle number 2. But now see, what am I doing to these little rectangle areas? I'm adding them up, because we're totaling them up, because we're accumulating. And so now rectangle number 2 is going to be having height, whatever comes out from f at 0.25 times 0.25. So height times width, height times width. Okay, and then rectangle number 3 is f at 0.5 times the width 0.25, and the last one is f at 0.75 times the width 0.25. All right, so 4 little rectangle areas being added together. Okay, It will give us an answer. It will give us an answer. But now I have to tell anyone. Look back at the picture again. So we found an accumulation of the 4 little sub-rectangle areas. But even if we added up all of these little areas here, does that give us the exact area inside of the bent curve here between the curve itself and the x-axis from 0 to 1? It did not. It did not. There's still a little space here that we did not cover. So the rectangle only covered these part being shaded here. It still left out these white space. Okay, it still left out these white space right here. But at least let's do the best we can do, and that's why I said earlier we're only approximating. And so now let's call the whole area here, the whole area that I brought up as the goal, and I already erased the goal of our problem here, but the whole area. Okay, so the area, the exact area, let's call it area. But now this is not the exact area. This is only the area that's obtained by accumulating the little sub-rectangle areas. And we got the height of these by specifically choosing the left endpoint on each subintervals, on each of the subintervals. So in that way, now allow me to introduce a symbol here. Now I introduce. Later on, I'm gonna get more formal into that. But now all that work here is called. I'm going to start to be into the informal a little bit. The Riemann sum value. It's a sum, okay? And to be honest, Riemann was not the first one who came up with this idea. It was, like I said, Riemann is one of the modern mathematicians. I consider that already. But he's actually the one that formulated into an idea. People in the past came up with that idea long past ago. They came up with that idea, but they never have a solid. They didn't have a solid formulation up until the time that Riemann really came up with that and gave a solid generalization. So for now, this sum that we created here is called a Riemann sum, and symbolically throughout many textbooks use a capital letter L, and we broke the problem down into 4 subintervals. 4 subintervals. Recall from the beginning picture. So capital L 4 here. So this means, and as I said, right now. It's just a brief introduction, and we will get formally into understanding what exactly a Riemann sum is. So for now, it's just what we did there throughout the activity. Up until this point, summing up the little sub-rectangle areas, 4 sub-rectangles, right? And we chose a left endpoint. And that's why it's a capital L here, stands for left endpoint. It's a Riemann sum, but using the left endpoint rule, okay? So L4 here. For short, people also refer to that as left Riemann sum. That's what it is for now. And L4 is the symbol for it, the symbolic expression for that. All right, so now we are ready for the actual calculation. And so L4 will be, okay, so now let me write it down a little bit. The height here is indeed 0 square times, so L4 can be calculated that way, 0.25 as the width, okay. How about and then plus, and then I thought I was about to go into a slightly different direction, but let's hold that idea until the next one. That one is going to be 0.25 square times another 0.25. This is going to be 0.5 square times 0.25. And the last one here of ours is going to be 0.75 square times 0.25. That's the setting up for our calculation. So 4 separate terms. And now viewers can go ahead and pause the video and have a quick calculation on your own right here. Just when we're at the very starting step here, then it takes time. It takes time to get through with this. Okay, and I'm quickly gonna step away from my own calculation, and I will be right back. All right, so now I have after I've made my calculation, my L4 here, the Riemann sum using the left endpoint rule, or for short, the left Riemann sum. My left Riemann sum calculated to be 0.75 21875. Let me double check with my calculation one more time. All right, so it's all checked with my calculation. So left Riemann sum calculated based on 4 subintervals, and that from that there it's produced 4 subrectangles. It's 0.21875. Okay, and so now I'm telling anyone viewing this video, this is not the exact area yet. You can see that through the picture. And again, the picture is here, and I had to partially erase it. But see, this whole area between the curve and that x-axis is not exactly what we have found, because what we have found is only the accumulation of all the shaded picture here, and we still left out all of these some of these white spaces there that didn't get covered. Okay, so now this whole area I'm aiming at is not exactly the L4, and you can see through the picture that it's a little, the L4 we calculate was a little less. And so now we can say that at least if we don't need too much precision, then the area we're aiming at is approximately or close enough to L4. That's the idea. Okay, and so now take it slow. You can go ahead and rewind the video, but I believe I have gave all the detailed explanation as much as I could already. And so that's the whole idea of running a Riemann sum. And of course, I still did not get into the formal definition of what a Riemann sum is yet, but you can already start sensing through the steps how we're doing it. The Riemann sum came out from the idea that we break our total interval into subintervals, and then we set for ourselves into picking the left endpoint on each subinterval to create a rectangle over it, kind of like a numerical, a visual illustration of that. Okay, and so now before I head out to the next problem, let me show you that that picture on the computer screen I have here, which is a very interactive tool that demonstrates the whole idea, and it gets the exact picture right there. So this is the exact graph I was doing on the board the whole time right there, and allow me to skip all of the grids on this. It's on exact scale right here, the 1:1 scale, and so the interval that we're looking at is here. So now let me show the interval on my graph. This is the interval. So it starts at 0, okay, and it ends at 1 right here. That's the interval. See, then when I click on that point, it gives me 1, 0, which is that interval. All right, and so the starting point is 0, the ending point is at 1, and then remember that throughout our activity we were breaking the total interval here into 4 subintervals. So this is how I show the 4 subintervals. My software I'm using here, I'm particularly using Desmos, the graphing calculator with Desmos right here. And so I have not found an effective way to put the labels here, because this is my own customized labels instead of using the actual numerical label on the axis. So here in this picture I don't have the numerical labels, but 0 is here, 0.25 is here, 0.5 is there, and then 0.75 and 1 is here. Okay, and so as I said, we chose to go with equal width, so the machine is doing a very good job of breaking it down into equal width subintervals. And then now the left Riemann sum, the whole idea. Now I'm going to bring up the picture, and instantly everyone is going to all see that. There we go. So this is rectangle number 3, that little space right here, because see, if we substitute 0.5, which is the left endpoint of this particular interval, into the function, and this curve right here is a function for x squared, in case I forgot to mention it. So 0.5 substituted into the function produces this height for us, and from that height I'm going to draw over as a rectangle, and that's how I did that. That's what I did in the activity on the board earlier. And so this height here is f at 0.75, 75 or 0.75 squared, the left endpoint on this fourth interval. And this is as a picture of our fourth subrectangle. And our subrectangle number 2 is here. On this interval, the left endpoint is at 0.25, and I'm using 0.25 substituted into the function, and that's how I got this height. And so I enjoy doing this decimal because it has a really precise graphing calculator, a feature that does all the nice graphics for us, and it can also do a lot of calculation for us as well. And so this very first rectangle, in the way how it looks, even with machines, in the way how it looks, it has to be just simply a line, and I can just quickly zoom it in, and no matter how far it is, that rectangle is not going to rise any higher because it's height 0, as we already nailed down with the calculation on the board. Okay, and so the summing up of all of these rectangles out there, right there, gives me that final value to be. And right now I'm using 4 subrectangles. So that final value was calculated on the board earlier to be this value, 0.21875 right here. And to be honest with anyone viewing this video, I actually also had decimals calculated this value for us. And so that's how it's heading. So I'm going to take some time because everything we have done is only half of our journey, or maybe just 1/3 of our journey in terms of having a full, complete understanding of what a Riemann sum is. Okay, so now I'm going to erase this and possibly the whole complete picture because and reconstruct the exact picture in a different way. All right, but of course, a lot of things we have done when we were doing, in what we were doing earlier, can be retained, in a sense that it's the same generality that we're going to break it down into 4 subrectangles here. And yes, that's my picture. All right, so these are the partition points. Their values won't change. Their values of the partition, it won't change. We're still going to stay with 4 subintervals. And let me put away all of these extra stuff here. Okay, we're going to break that down into 4. We still stay with 4 subintervals, and we're still going to decide to go with equal widths right here. But so earlier we were looking at left endpoint rule. We were setting for ourselves into left endpoint rule. So what about the right endpoint? I mean, because what I said earlier, maybe it was just me that I love to start out with the left endpoint, but other instructors, when they're teaching this exact material on each subintervals, they also can have their choice to start out with the right endpoint. And at the end of the lesson here, right endpoint or left endpoint is just a choice. And at the end, it's all going to give I'm not saying exactly the same result now, but in the long run, it's going to produce the same result. And so for now, let's look at how about what if. Let's just think about we're doing some experimentation here. Right endpoint. Okay. So let's pick interval number 3 here. Okay, interval number 3. This time I get a little more clever that I put the label below here, so so I won't have to erase too much. So in this interval number 3 right here, because it is the easy one to see in the picture, instead of choosing the left end on the interval, as in the earlier case, now I'm going to purposely choose the right end. So the right end on this interval, still 0.5 is the left end, 0.75 is the right end, but now I choose 0.75. I'm going to substitute the right end into the function as usual. So now I'm going to produce a height, 0.75. That's the right end of my interval number 3. And I'm substituting that into the function. It's going to give me for sure 0.75 square. And this, I call this here the height. Okay, that's the height of my, because see, once I put that in there, I'm going to get something like this. Yes, it gives me a height. But now the interval I'm looking at is interval number 3 right here. And so if I treat that as a height, then I'm going to have to draw my rectangle as following. I'm going to draw over. You see how it happens right there? You will see how it happened as I finish my drawing. Okay, there's my rectangle. And so this time my rectangle is kind of above the curve itself right there. Okay, but see the height of the same interval. But now we're going to draw the rectangle over it by producing that height being the height from the right end point. All right, so that's the idea right there. So that's height. The width is the same, 0.25, because that's the space, the width of your interval. And then we call that namely the delta x value earlier. Okay, and so now in that way, yes, one more time, if we multiplying this known width with the height that we have just obtained, we will get that the area shaded there in my rectangle number 3, my subrectangle number 3. Okay, and so same idea. I'm going to move out to the other board. Quickly note down what happened there. But this time recall for yourself that we use right endpoints on each subinterval. All right, so rectangle 3, the height was f of 0.75 and the width was 0.25. Okay, so height in product with width, that's my area for rectangle number 3. And that's the part being shaded in the picture earlier. Okay, and so now let's look at little subinterval number 4. And again, I decide to put my label at the bottom now. Left endpoint is here, just like that, just like before. Left endpoint is at 0.75, right endpoint is at 1. But this time I chose to use a right endpoint on that subinterval and substitute that into the function to obtain my height. So my height is indeed this height right here this time. Okay, and so f of 1, that's graphically the height of our rectangle here. And from there, yes, it's 1 square numerically, and we call this is the height. I'll leave the calculation for the later step. And from there, I'm going to draw back to the left my rectangle. Okay, and so my rectangle again will have a width equal 0.25. And then that is the delta x value that I put in parentheses here. And so if we now multiply 0.25 with 1 square, that will give me the area that I'm shaded here. Shading here, and that's the area for the subrectangle number 4. Okay, so now at this point, having some experience after working with left endpoint rule, and things can start speeding up a little bit, and you can sense it. All right, and feel free to even fast forward my video if you feel like the steps you're doing here, you're already ahead of me, if you feel so. So rectangle number 4, height is f of 1 times 0.25 being the width. Okay, and then so now I'm turning quickly into my rectangle number 2 right here. Okay, I put my label a little too close to the other. Okay, rectangle number 2. And so in this subinterval, see, it all started out being a subinterval, and then the rectangle rise on top of that. Okay, and so now in this time, I'm going to choose my right endpoint, which is being 0.5 here. So right endpoint is the 0.5 for this second subinterval. And so that means now I'm going to substituting 0.5 into the function. Yes, it's 0.5 squared. It will give us some value. We call this the height. Okay, and then the width for this. So that's the height. The width for this is 0.25 again. Okay, so where will that picture look? I mean, where will that picture be? It's like that. All right, and so now multiplying the width, the height with the width here. And that width is the delta x. Now, this parentheses here is just indicating as a comment right here, but it doesn't mean 0.25 multiplied with delta x. Okay, but now multiplying the width with the height here, it will give us that area. So 0.5 square, that's the height, multiplying with 0.25 the width, that's the area for this little picture. Rectangle, subrectangle number 2 right here. All right, and so now I'm going to again move out to my other board, and I'm recording it down for rectangle number 2. And I also became a little more clever in terms of partitioning my space here on the board to make things go a little better. So this is f at 0.5, okay, and times with the space with the width, 0.5, and I mean 0.25 here actually. All right, and so now it's the last. It's actually the first, but I'm handling it last because it's so little. So for rectangle number 1, for subinterval number 1 here. All right, we choose the right endpoint on that subinterval. So right endpoint is a 0.25. Substituting 0.25 into that and drawing that over as a rectangle, I have this little rectangle. So now, here's on quick scratch work. We're looking at, see, f at 0.25, or laying it down, 0.25 square. That here is the height. Okay, and then the width here equals 0.25. Not the spot, it's the space here. And that is the famous delta x. Multiplying these two quantities, giving us this setup right here, 0.25 square times 0.25. But this will be the area shaded for that first little rectangle like that. Okay, so in that way, for subrectangle number 1, the first one from the left to the right, we're looking at f at 0.25 and multiplying that with 0.25. Okay, so 4 little so these are all 4 little setups for the areas of the subrectangles. Okay, and now in that way, as I keep saying earlier, the idea now is that we're going to be accumulating all of these areas, all of these little sub-rectangle areas that we produced. Okay? And so now I keep saying sub-intervals, sub-rectangles, but the rectangles itself go above the curve. I had students questioning me that, the professor, I mean, why are you calling these sub-rectangles, but the picture actually stays above the curve. Sub-rectangles just mean the kind of rectangle we produce from the sub-intervals. Okay, but it doesn't necessarily mean the rectangle have to stay below the curve. It doesn't always have to be like that. Okay, and so because the curve is here, see, now I'm going to have to redraw the curve there. But now, as a big picture, again, we're going to sum up. And see, that's where Riemann sum is waiting ahead for us. We're going to sum up, okay, all of these, or we're accumulating up. Okay, we're accumulating up all of these little sub-rectangle areas. All right, so now again I'm going to navigate to the other board. Okay. And so, rectangle number 1 is 0.25 substituted into the function times 0.25, the width. Rectangle number 2 is 0.5 substituted into the function for the height and times 0.25. And as I said, summing up or accumulating them. That's why we're now adding all of those little areas together. That's what it is. So plus, next one, 0.75 substituted into the function to get height, multiply with 0.25. That's your area of the third rectangle, sub-rectangle. And then we're going to add the last one here, FF1, multiply with 0.25 right here. Okay. F at 1 multiply with 0.25. And so now I introduced this symbol again a little informally because it's ahead of time when I actually gave a formal definition. but this is called R4, a capital letter R, R4. So that's how we're setting it up, R4 here. So what exactly is R4 again? This is how we call it. This is it's a Riemann sum, but it's a right endpoint Riemann sum. Right endpoint Riemann sum. Okay, and so as a matter of fact, now when we get to doing the actual calculation, then we need to really work out these values right here. Working out those values going to give us, let's say, first one is a 0.25 square times 0.25. Okay, and then we're moving on to the next one. It's 0.5 square times 0.5. Okay, and if anyone can go with the some algebra way that can make things run a little faster, you're more than welcome with that. And then here is 0.75 square times 0.25. Okay, I'm running a little bit short of space here, so now it's 1 square times 0.25. 4 little rectangle areas being accumulated together. Okay, and so all right, so now after my calculation that I used with decimals, my R4, my value for the Riemann sum using right endpoint rule, 0.46875. All right, and so we got the answer, but I have to again emphasize, just like when we were doing the left Riemann sum, and so here I emphasize it again here. This is the answer for R4. It's the answer for R4, the right Riemann sum, because that's what we did. We summed up the areas of the little subrectangles, but the actual area that we're aiming at is not precisely the answer we have just gotten now. So that area we really are aiming at, the area between the curve and the x-axis, and between 0 and 1 right here. You can see in this picture here, if we're using the right endpoint rule, then the right endpoint, the right end Riemann sum is a little bit above or a little bit over, right? We got these extra shaded area here outside of our main aim right there. So in the end, it's still not our exact area that we're looking at here, but it's only, we can use that as a different way of approximating it. So in this case, this approximate is a little over, but in the end, again, the area, now I say that the area is approximate, can be approximate by R4. That's all I can say right now. So R4, I have to keep making it clear, R4 is not exactly the area that we're aiming at. It's only an approximate, and we use 4 sub-rectangles, 4 sub-intervals. Okay, all right.